All right, good afternoon to everybody who is currently in today's session. We had already seen an introductory list of concepts that had been identified for this particular course during the previous session. Okay, so when it comes to the role that avionics plays, which has gained significance over the course of several decades since the first of the mainstream aircraft types had taken to the sky. In the previous session, we had looked at some of the factors that serve as driving influences in the development of and the deployment of avionics systems on board routine types of aircraft. Okay, and the broad classification as far as the mission attributes are concerned has to do with whether they conform to aircrafts of the civilian kind or of the military kind. Okay, so depending on whether it is put into active war services or is it meant for peaceful activities. So that is the primary classification. And when it comes to a class of aircrafts that belong either to the civilian or the military type, depending on that, there are varying types of driving factors. Okay, so we had seen the case for civilian aircrafts and the factors that have driven avionics to assume a pivotal role, and these have been in the form of converted benefits. Okay, economy wise, in terms of the training requirements, in terms of the salaries meant for the crew members, and evidently the actual numbers of people who can be replaced. Okay, in the event you have significant level of automation that has been identified to replace the onboard crew. Okay, so in a place where you have 3 and 4 people in a cockpit, which is the nerve center for the avionics system, you will now have possibly 1 or 2 of them. Okay, and at times it has gone to the extent where even a single human element at the controls of the aircraft can in fact be relieved for a duration of time, and the aircraft can literally fly on its own. So those kinds of benefits evidently on the civilian side have been a driving factor for enhanced deployment of avionics on board aircraft systems. Now let's look at the strategic side of avionics. Okay, and primarily, if I have to tell you a particular aspect of how avionics has developed, it has primarily been in its forefront taken over by strategic applications. Okay, so the actual import of how much avionics has developed over the course of time is primarily been identified in a very large measure by the typical inputs to technology derived from the strategic or from the military side of aircraft systems. So in the military case, the driving factors, if we were to look at that side of things, in the example that involves a single seat fighter airplane or the so-called attack aircraft or a strike aircraft, okay, replacing a second pilot with an autonomous method for control and mission aspects driven capabilities of the airplane will evidently mean you have less cost, because the requirements to support a human element on board technically superior environment such as an airplane is going to be even more rigorous. Okay, life support is one aspect which brings with it quite a lot of technical add-on abilities that have to be carried on board the airplane, which in turn translates into enhanced weight. So for example, you'll need to have breathable quality air with rich oxygen presence, ability to support them logistically speaking in terms of food and requirements to keep the human being on board, okay, in a level where it is acceptable. So those kinds of elements mean you'll need to carry extra payloads on board aircraft. So that can certainly be removed if the second human element in fighter airplanes, for example, is also made optional and completely removed away from the cockpit scenario. So in the case of fighter airplanes, where the crucial element is performance of the aircraft, it is a very nimble and agile airplane. It has the ability to perform extreme aerodynamic maneuvers, adding more weight in the form of a second human being, and the support system for such a human element can certainly be done without. So in this context, you have the two-seat version progressively getting replaced by a single seat or an optionally piloted scheme of aircraft systems. Okay, the cost evidently has reduced as an outcome of this. And what role had previously been played by the second and the further crew on board attack or strike aircraft systems is now been almost entirely taken over by autonomous systems. Okay, and that in turn requires electronics and software to closely work in synchrony in order to achieve the equivalent performance of that of a human being. So elimination of the second crew member in the form of either a navigator or an observer or an engineer, flight engineer, is certainly advisable because of the evident advantages it gives for the aircraft's performance in terms of either an extended range it can travel, considering that replacing a human being with an equivalent weight of fuel means the aircraft can travel a further distance. Or if it is a mission that requires additional payload to be carried, such as reconnaissance and surveillance equipment, or for example, additional ammunition, okay, in the form of missile systems and so on. So these are all possibilities that can be now explored, given that there is now a lack of a second human element on board the aircraft. Okay. Additionally, this also means you have a reduction in the training costs because you'll need to only train a particular pilot, and the training that goes into a second pilot's presence in an eventual airplane can now be completely removed away, because most of that is replaced by electronic systems which can capably handle it without the element of fatigue, okay, which is a big worry in the case of human beings. So over an extended mission duration, it is very likely that human elements suffer from a fatigue or a progressive degradation in performance. So that is unlikely to be the case with electronic systems. Right, so there are a few other very important driving factors that have progressively resulted in incorporation of additional avionics system on board aircrafts. Okay, first and foremost, reliability and safety considerations. Next is requirements with reference to ground systems that have to support the aircraft. Examples include air traffic control requirements. Okay, if there are multitudes of airplanes clearly beyond a point, any number of human beings who are located on top of a very vantage point air traffic control tower will really have less inputs to provide because of the sheer numbers of airplanes that have to be considered in a given region of airspace. So that evidently means reliability, safety, and requirements set on air traffic controls can also be progressively reduced. The next one that we'll need to carefully monitor is the case of all-weather operations. Okay, nowadays airplanes have the ability to perform without being restrained or severely constricted by the ambient weather conditions. Okay, all-weather capabilities are one more attribute which have gone into the design of airplanes themselves. So evidently, a lot of instrument related inputs need to be derived for this from the external world in order to safely navigate the airplane in inclement weather. The next point that has also served as a driving factor is the reduction in the amount of fuel that can be consumed, okay, because of evident reduction in weight associated with the additional human elements that have to be carried on board. And the last one that has to be told is about the improved aircraft performance and control and handling, in addition to the reduction in the maintenance cost that is involved. So with all of this evident benefits that have gone side by side, you can certainly notice that including more electronic systems on board has certainly been of significant advantage in aircraft systems over the several decades of evolution in the aircraft technology. When it comes to military case, having seen the civilian side of additional driving factors, let's also look at the military aircraft systems and the avionics that are used in such kinds of aircrafts. What sort of a driving factor exists here? Okay, so the avionics systems, in the case of strategic or tactical aircraft systems or military aircrafts, consists of the nature of the threat to which, or the nature of the threat perception, or the so-called danger that the aircraft is being exposed to. So there are varying degrees to which the aircraft dangers can be classified, depending on starting with either the aircraft operating within the its own territory, or if it has the ability to cross the boundary into hostile territory. Okay, so depending on that, a wide cross-section of threats can be identified. So depending on that, you have the aircraft capabilities, which can be classified primarily as defensive type or offensive type aircraft. Okay, and what capabilities that the aircraft have when it eventually comes across a potential aggressor type aircraft, which has already invaded the homeland and is trying to find out a few targets to neutralize. Okay, how does one stop such airplanes? So that is again a case where it is at a point in time when human elements and their abilities to detect such airplanes within the small closing timescales that are available among a pair of airplanes is concerned is extremely limited. So you do not have human beings able to make very confident and accurate decisions, especially if the aircrafts are flying against each other, one belonging to the homeland, the other one of the adversary, flying towards each other at speeds which are in excess of about 3,000 kilometers per hour. Okay, like for example, each one flying at Mach 2 kind of speeds. Mach 1 is the speed of sound, 330 meters per second, and so on. Okay, so that translates into something which is significantly high in terms of the kilometers per hour. So if you have two aircrafts flying towards each other at extremely high speeds, in a matter of seconds, there is a chance to either detect the airplane or completely lose sight of the aircraft altogether. Okay, so those abilities are severely limited for human beings, and you will need instrumental aids to support the human element in detection as well as stoppage of such aircrafts coming into homeland. Okay, so these are potential aggressor airplanes, and offensive capabilities really have to be up there in order to match the hostile aircraft's capabilities. All right, let's look at the typical evolution in the type of electronics that has gone into the avionics systems over the course of the past several decades. Okay, and this evolution has either remained in currency over several decades or has shown a tendency to move into a new level of technology with every progressing 2 to 3 decades. Okay, so that's exactly what we see here from a case which had since the inception of aircrafts and their abilities to fly untethered in three-dimensional space, starting with valve-based schemes or thermionics methods for implementing logic systems, okay, that can do a certain degree of computation. Thermionic valves were the first schemes that were ever available, and they had certainly shown their immense capabilities all the way till about the 1960s. Okay, and even today, most of this electronics is actually rated against the standard that has been set by the thermionic valves. That's primarily on account of the robustness in performance and the less levels of inaccuracies that can be expected in the performance of such valve-based devices. So progressively, you also have various systems that have been incorporated based on such component level realizations, such as the airborne radar systems. So if valves were to be really bulkier, their abilities to be carried on board aircrafts becomes a lesser possibility. That's primarily because aircrafts have a definite amount of size and weight carrying ability, and they also have a severe constraint in terms of the amount of power that they can actually take on board. Okay, so in order to energize the various electronic systems. So if you will need to incorporate sophisticated solutions of avionics such as radar systems on board aircrafts, you will need the electronic components to be miniaturized, because that's primarily the reason why there has been a transformation from valves to transistor-based systems, semiconductor devices, okay, from the valves to the solid state type. Okay, so that's the imminent possibility that has resulted in the incorporation of radar systems and various other electronic avionic systems on board aircrafts, considering that there has now been a transformation in the component level. Okay, so you also have a corresponding change that has been brought into the signal characteristics. So from an all analog type, there is a progressive transformation into the digital type of signals. So digital aircraft systems have been the advent of all the progressive changes to technology that have taken place beyond the 1970s or so. Okay, so that's when you notice the actual support structures for the transistors available in the form of signal parameters, which are already getting digitized. Okay, with more transistors per square inch getting defined on the semiconductor device, you now have a chance to do massive amount of computation. So that's the idea of the digital aircraft system. You also have a large and very large scale implementation possibilities, and the concept of the multi-chip modules. Okay, multi-chip modules are in effect a combination of passive components such as resistors, capacitors, and so on that reside side by side with the active electronic systems, okay, which are able to do memory-based or computation-based activities. So that is the evident benefit that has been attained out of use of large-scale integration, where you have the possibility to define progressively reduced scales for the track and the space attributes in wafers. Okay, wafers are semiconductor materials which are used in turn to fabricate large numbers of application specific or field programmable ICs. Okay, so depending on the context, whether you want to use it for memory or for computation, you have the abilities to create massive numbers of such smart electronic devices and incorporating all of them into a single substrate, be they of the integrated circuit type or be they of the components type, such as resistors, capacitors, and so on. So the availability of all of this on a single substrate is evidently the concept of the multi-chip modules. Okay, so that has been the most recent of the transformations that have taken place, and since the new millennia. Okay, so over the course of several decades, you can evidently notice the major developments that have taken place in the avionics systems that are carried on board aircrafts. So this is just to give you an idea of what an MCM concept is. So you can see evidently a lot of memory devices, application-specific ICs, and so on, in the midst of which you have all the chip capacitors and so on. So this arrangement of various components, depending on the nature of the avionics system, which will require such an assembly. so that in scenarios that involve development as well as troubleshooting of a malfunction part, you have an ease with which the access to a particular subsystem's functional electronic block exists as part of the design itself is called as a hybrid IC, or also called as a multi-chip module. In order to give an understanding of how the progression in the packing factor of critical electronic components has been over the course of the same time frame, or almost a similar time frame. So you have this particular chart which indicates the packing factor, or the so-called packing density of the transistors and the cost that is involved. Okay, progressively the cost has tremendously scaled down to a point where it is cost effective. At the same time, you can also see that there is a significant number in terms of the square area that is occupied by multitudes of logic devices. Examples include transistors of various types. Okay, that could be used as memory storage buffers or as flip-flops for the purpose of computation and so on. Okay, so independent of the case, in its most recent version, the Intel Core i10 has scaled to a sub 2 nanometers level in terms of the space occupied by a single transistor. So that's the most recent advent in terms of how technology has progressed, even beyond what is being indicated in this particular chart. Discussion further on this topic of how the evolution in avionics has taken place, not just in the area of transistor technologies alone, but in various other regions of the total ecosystem called the avionics solution. Okay, so the initial stage developments had primarily taken place in the area of applications of avionics and electronic systems to airborne platforms, such as their confined presence in analog devices and systems, and also with signal levels and voltages that are generally related in some linear or predictable manner. So that is how the initial developments had been. So systems of this sort, which are by and large of the analog kind with very predictable performance characteristics, are mostly susceptible to or are affected by concepts such as heat dissipation. That in turn causes the device to actually progressively shift in its performance, which is called as the drift. So that term drift is used to actually indicate the progressive shift in the optimum performance attributes identified with electronic systems on account of the heat that gets dissipated within the overall system as the various components operate over extended durations of time. Okay, so the drift can certainly be of various kinds. They may be predictable, in which case you could do some corrective aspects to the performance, or they may be totally unpredictable in nature. Okay, totally statistically defined. Another kind of performance malfunction is also called as non-linearity, which means it's a performance away from a predictable or linear behavior type. Okay, so these are all some of the aspects that are driven by heat dissipation within the device on account of the less refined level of fabrication that has gone into the performance and the deployment of such devices, okay, which by and large work on the analog signal type. And most of these analog devices certainly have drawbacks in the form of drift and non-linearities. Replacing such analog solutions, you had at some point in time what is called as a digital computing environment taking over. So the theoretical framework for it was pretty much well understood over several years, and it had a direct application for aircraft systems, considering that they already had made a significant advent in commercial electronics, okay, household electronics and various other terrestrial systems which made use of digital computing solutions for immense benefits that could be derived as replacements to the analog type. So the development of thermionic valves, also called as vacuum tubes, enabled digital computing to be accomplished, although the realizations of this in hardware required extreme large space and took quite a bit of onboard power to be realized in terms of their functional attributes. And they were also very costly considering the rarity of such components. Okay, so the overall system was physically enormous and was extremely impractical to be carried on board aircraft systems, considering they were massive, heavy, and also consumed a lot of power and were evidently costlier. So they were extremely rare in their presence, and if at all they were there, they occupied quite a bit of space on board the aircraft, typically nullifying the advantage that was likely to be provided by them as replacement solutions to human beings. Okay, so the arrival of transistors was the best possible replacement solution that could, in one shot, do away with both human beings as well as the massive components which were deployed in the form of vacuum tubes. Okay, various other derivatives of the transistor technology, such as semiconductor-based devices, evidently led to what is called as an optimization metric, which is something you'll also have to keep in mind always, the so-called SWaP-C criterion. Okay, advantages in size, weight, power, and cost. S, W, P, and C. SWaP-C is one of the important metrics in avionics systems that is used to rate the performance of a particular solution against a competing vendor's product, depending on how much space they occupy, what is the total weight that they contribute, how much of power they utilize, and what is the typical cost involved in deploying such a solution. So the concept of SWaP-C is very integral to the choice among competing products in avionics systems, among which one has to be certainly chosen to be carried on board the aircraft. Okay, with the advent of transistors and various similar sorts of semiconductor-based devices incorporation as avionics solutions, you had the advantage in the form of a massive SWaP-C improvement to the existing valve-based and analog type schemes for avionics implementation. Okay, so digital technology is the actual current version of how avionics systems have been implemented in significantly large sections of aircraft systems, which have to do multiple roles depending on which they are primarily chosen and deployed to carry out the specific roles. Okay, and this have increasingly used control of aircraft systems as well as mission related systems as the primary elements for realization of the various missions. Okay, you'll need to primarily ensure that the aircraft remains airborne and has a reasonable ability to remain survivable despite possible damages that the aircraft had sustained, especially during warfare. Okay, so that ability to remain in survivable mode is primarily realized in the form of control of the aircraft's flight characteristics. Okay. Additionally, crucial mission-related systems also need to be optimally performing because the aircraft has in the first place been put into air to carry out a certain mission, okay, or a certain program for which it needs to completely lend its support. So in order to be survivable as well as be mission ready, the aircraft's readiness is primarily uh, improved quite a bit with the advent of digital technologies. So a key driver in this application has been the availability of very capable and reliable as well as cost-effective digital interconnect solutions, also called as data buses. Okay, data buses come in various standards, and this primarily serve as the backbone onto which various components and subsystems can be linked. So it's like the highway on which immense amount of data transport takes place within the aircraft. Okay, and at times it also spills beyond the actual skin of the airplane to regions which are either space-based or ground-based communication systems. So in any case, you have a communication linking ability that has to be identified as part of bringing together the various components, considering that most of these components or subsystems are manufactured by various companies, or the vendors for each of them is different. So in effect, the aircraft is like a fusion of so many technologies, all helping with simultaneously realizing survivability and mission capability. Okay, so some of the examples of this data links or the so-called data buses are the American Radio Incorporated, ARINC. Then you have the military standard, MIL STD. Okay, so ARINC 429629, MIL STD 1553B. So these are some of the examples of data links or data buses. We'll be looking at these data buses in greater detail as part of the coursework discussions, somewhere closer towards the middle section of this course, okay, which means possibly about 15 classes away from now. That's when we will have a thorough discussion starting on this concept of the data buses. So there are data buses of various types. They may be either wired or wireless, either types that use metallic and dielectric type transmission line elements or waveguides, or they can also use optical fiber cables. Okay, so depending on the choice of the suitable data bus, there are varying kinds of advantages that each of these offers. And a typical aircraft will carry a few types of these data buses depending on the nature of connectivity that has to be enabled in a small part of the aircraft subsystem or for the entire aircraft assembled out of multiple such subsystems. So digital technology, when coupled with the availability of cost-effective computing solutions such as microprocessors and more advanced software development tools, has led to the widespread application of avionics technology throughout the airplane. So this has advanced to a point where virtually no aircraft system has been left out of the service offered by avionics solutions. So avionics technology is also influenced by external factors, let alone by the primary driving factors that we saw a little while back. There are also factors beyond the actual scope of aviation, which have also strongly influenced the avionics technology in a significant manner. And these are factors which are external to the aerospace industry altogether, okay? Be they of the commercial type or the military type or the space-based avionics systems, okay? And this have resulted in a drive towards even more exciting standards in terms of the performance of the avionics system. So this is primarily measured in terms of the performance realization of the airplane, the reduced crew workload that has been evidently observed, and the safety improvements as well as supportability that can be derived out of use of such avionics systems. So in terms of the outcomes of all of these activities, what is perceived is, in the case of civilian aircrafts, passengers find that the aircraft utilization to which they have actually solicited a certain activity, such as either carrying themselves from one to a different location or sending a cargo from one to a different destination, has become more reliable. Okay, there are lesser numbers of delays or cancellations of the airplanes, and the evident benefit in terms of the comfort levels that have been achieved using avionics systems is also one more attribute. Okay, compared to the very first order schemes of air transport, wherein you had everything which was in a crude form of implementation with no creature comforts or any of the additional facilities that could be offered by current day aircraft systems. So if you were to make a comparison among the two, it becomes very evident that use of avionics systems in various roles and sectors has resulted in reliability, less delays and cancellations, and more comforts that have been offered because of their evident incorporation. So external factors, if we were to look at it, they come in specific forms. Okay, both the commercial as well as domestic electronics equipment market is dominated by advances in telecommunication, which have in turn taken their cues from miniaturization, computing, and display technologies. So, for example, you needn't actually, as a matter of fact, rely on large format displays to be available on aircraft. So today, what is typically noticed is, especially in business jets, which are likely to carry less number of people on board, the pilot comes with pilots come with their own tabs, okay, which they can seamlessly integrate into the onboard aircraft electronics and perform various kinds of roles, okay, or monitor the critical capabilities of the airplane as an interactive two-way control as well as monitoring terminal. Okay, so those kinds of application programmer interface or API scheme is very evident in its realization because primarily it has been taken out of the domestic electronics equipment manufacturing process, such as the solutions offered by Android or Apple tab developers. Okay, so those technologies can actually be also used in a seamlessly integrated approach to avionics systems. So the advances have primarily happened in the sectors such as telecommunication sector or in the semiconductor manufacturing schemes or in the computational side and display technologies as well. And these are getting incorporated into the aircraft aerospace system design as well. All right, so now let's take a look at the typical classification approach that exists in terms of how microelectronic devices used in aircraft systems can primarily be identified with one or the other side of this particular chart. Okay, so you have evidently the real world and the digital world. So the real world is analog, where the information is available in a continuously variable form, which can be broken down into an infinite number of parts. Okay, continuous meaning depending on how fine a sampling you can achieve, you have still the presence of information without any loss. Okay, so that's the idea of the real world. So it is called the analog information, and it is used to monitor various parameters in practical world circumstances, such as, for example, if you want to monitor the temperature outside the airplane, the wind speed, the speed of travel of the aircraft with reference to the wind blow direction. Okay, so the density of the atmosphere, which in turn will critically influence the ability of the airplane to fly at a certain height. If the density is very thin, the aircraft has to drop down to a denser region of the atmosphere so that it is able to obtain the necessary purchase in its power plant, okay, which is in turn going to decide how fast and how able the aircraft will be flying. Okay, so those aspects are all in the real world. They'll need to be constantly monitored. The temperature is again one more aspect which will in turn influence the density of the atmosphere. So analog information needs to be converted into a form considering so many parameters that require to be monitored. It needs to be converted into the digital type. So analog to digital converters and conversion schemes need to be adapted. So that is effectively what you see at the bottom, where you have ADCs performing the role of transforming the information into a discrete series of data, okay, which are at some level reasonable representatives of the continuous world data. So you cannot say that they are entirely very good, because when you go for discretization, there is the evident possibility that some information from the continuous world is getting totally lost, because the information is constantly being sampled at discontinuous intervals. Okay, so you have broken pieces of information. So that information is either in the form of the critical data part, or the precise location where this data has to be identified on board the computing system. Okay, so you have lots of memories of various types, processor side memories such as the cache and so on, and the exclusive memories for the uh, storage of results of intermediate algorithm processing, or the final information processing, or the raw data storage itself. Okay, all of this requires specific regions of memory to be identified, and the addressing scheme is meant for that. So you have the collection of both these, which constitutes what's called as the word or the message, and this message has to be processed after it is suitably been applied with the necessary algorithms associated with a particular functionality of the avionics system. An example of that includes a radar system that is carried on board the aircraft. Okay, so you have analog radio frequency signals which are sent and received. Beyond that point, all of the target parameters have to be understood with enhanced clarity by subjecting them to a computation. So there are specific radar algorithms which have to be applied for this, and these reside within the digital computer. So the data that has been converted into digital form is now applied with the aid of various algorithms in order to make some interpretation. So after the processing on the digital computing side is completed at some level, it has to be extracted out so that it can be uh, projected in a manner where human beings can investigate the outcome of this processing. Okay, so some display devices have to be used. So when it comes to display devices, again, these are of the analog kind, and the signals have to be reconverted back into the analog from the digital computing part. Okay, so that digital to analog conversions again take place and bring them back into a form that can be investigated by human operators of the aircraft. Okay, so along all of this, you have completely analog type implementation of electronics, totally digital type ones, as well as a hybrid approach making use of the multi-chip modules. I shall end discussions for today with this particular slide, and continue with further discussions on this particular topic, starting from here in the next session for this course, which will be tomorrow during the first slot, starting at 8:50 a.m. Okay, on a regular time frame, we will have exclusive discussions taking place. We will try to do a similar activity tomorrow during the first session for the course, which will be a continuation of the topic that we have seen in this particular slide. So if you have any queries or observations related to what we discussed in today's session, this could be taken up during the remaining time of about 5 minutes that's available. Arul Selvi, can you hear me? Arul Selvi, are you able to hear me? Roll number 107. All right, so please make a note. If I call out a specific roll number and there's no response, I will have to count the particular student as absent. Okay, so please make a note of this as well. Anupama, can you hear me? Roll number 205, Anupama. Dana Karthik, are you there? Could you please respond? Dana Karthik. Roll number 19, Dana Karthik.
Roll number 19, sir.
Yes, Dana Karthik, how did you find today's discussions? Were they completely followable, or would you need a certain amount of limited change that is allowable to be also included in this? How do you find today's session?
Yeah, it's good only, sir. I can understand well.
All right, so please make it a point to browse through extensive literature that is available online. At some point of time, I will be posting the discussions with a reasonable level of detail in these discussions so that all of you have an access for this. Okay. Harish, can you hear me? Roll number 218, Harish. Harish.
Yes, sir.
Yes, Harish, would you want to comment on what was the nature of the discussions we had today? Was it completely followable by you?
Yes, sir. It's fine, sir.
All right, fine. Thanks for the inputs. I'll also ask a few others. Nandini, are you there?
Yes,
Roll number
sir.
37, Nandini. Yes,
Yes, sir,
Nandini,
I'm there.
what sort of an observation do you have about the discussions we had in today's session?
So it is good, sir.
All right. Thanks for the observation.
Thank you,
I'll
sir.
ask Sridharan. Can you hear me, Sridharan? Roll number 247.
Yes, sir.
Yes, Sridharan. Can I have some of your comments as well?
Yes, sir. It was understandable and it was nice, sir.
All right. So Sridharan, and for the rest of you, let me also inform you that you will certainly have all of the slides plus the slides associated with the discussions put up in OneDrive pretty early. Okay. So it will be over the course of the weekend that you can see it so that you have a sense of what we are actually discussing in greater level of detail. So in the meanwhile, if you do manage to get hold of online resources of the type that we saw in the previous session, across 2 slides, we had seen quite a bit of textbooks and reference material. So if you have the ability to access some of this, that will also be good. Okay. Although the information that we are discussing in the course sessions is not totally derived from each of these reference material. As I mentioned to you, I'll be accessing information that is also not available in the public domain so that you are kept completely in the forefront of the latest developments that happen in this topic called avionics systems. Okay. Right. So if you have no further observations, today's session concludes on this particular slide. We'll have the next session for this course tomorrow.